The aim of this experiment is to perform some quantum mechanical calculations to determine various properties of carbon monoxide and carbon monoxide cation using two different approaches, density functional theory and the Hartree-Fock method. We're going to determine things like charge distributions, electric dipole moments, vibrational frequencies, and equilibrium bond lengths. And the purpose here is to show how powerful computational methods can be to supplement our experimental data. So in this video we're going to look at some of the technicalities of using Spartan and setting up your computational methods. So to start drawing the molecule, we can choose the build icon. It may be selected for organic. We're obviously drawing an inorganic molecule, carbon monoxide, so we choose the inorganic option. We're going to choose carbon initially, so we can choose the periodic table and select carbon, and we want carbon bonded to one other atom, so therefore it will be the single bond. So select this and draw somewhere on the green screen. This will draw carbon with a half a bond. We now want to connect that to oxygen, so I select oxygen on my periodic table. Again, I want an oxygen single bond, so I click on my bond and draw the carbon monoxide molecule. To get rid of the build area, we can just click on View. Now, if I shift and right click and drag this, I can make my molecule a little bit bigger. And we can see that if we click and hold on the molecule, we can rotate the molecule around so we can get a view from all sides. Okay, so now we want to set up our computational methods. If we go to Setup and Calculations, we want to choose the methods that we're going to run the calculation with. So we're going to choose two different approaches here, Hartree-Fock and density functional theory. And density functional theory will be chosen by this B3LIP option. So let's start off with B3LIP. We select equilibrium geometry, so this is going to optimize the molecule for its lowest energy state in terms of geometry according to these parameters as defined by B3LIP and this basis set. And the basis set really gives us a way of explaining what orbitals we're going to consider. We can click on infrared spectra, so this is going to give us information on infrared spectra. The total charge in our molecule is neutral, but when we come back to do the CO+, this is where you'll make that a cation. There are no unpaired electrons, and we're going to click vibrational modes and charges in bond orders, and this is going to give us this information on the molecule. So this is the first calculation that we're going to set up. So, having set up the calculation, we now want to set up what are called surfaces. These are the aspects of the calculation that we will be able to get some information on. So if we click Set Up Surfaces and click on More Surfaces, we're going to enter in three surfaces. The first one will be density, so I select density. The resolution will be high, so we want to select high or 8 times slower, and we press OK. Repeat this again, click More Surfaces. We now want HOMO, one level below the HOMO orbital, so we click HOMO minus, and the -1 here indicates that we're one level below. Again, our resolution will be 8 times slower, it'll be high. And finally, we'll choose our HOMO itself. You see here there's no option for 1 or 0 because this is the actual HOMO, and the resolution remains the same. So now I've entered in the three surfaces that we wish to calculate based on our calculation parameters. Once we've done this, we can now submit the calculation. So we can go Setup, Submit. So you can see here in the Setup menu we're going through these three phases. Calculations, to set up the initial parameters. Surfaces, to tell the computer what it is we want to calculate. And now Submit, we will click on to submit our run. So we can call it something sensible, so I'll call it Spartan CO run B3LIP. So this is going to tell me that this is the file for the density functional theory, and that is now running in the background. You can click Options, Monitor, and this will tell you that this job, as it's called, is running, and in about 10 seconds that will finish running, and this will disappear from the menu. But as soon as it has run, you'll see this pop-up message. So even if you don't monitor it, you will get a pop-up message to tell you that the run has been completed. Okay, so having completed the run, we now want to analyze what the output was. So we can click on Display. Okay, so again, look at the menus and look at what we're doing. We were in the build area, then we went into Setup, now we're going into Display. So we can click on Display and Output. And what have we got here? Well, when we look through the file that's spit out, the first area we see is an optimization. So if you remember, we said we want to optimize the molecule to equilibrium geometry. So this is the computer rearranging the carbon and oxygen atoms and optimizing the energy as a result. So you see here we get the lowest energy. It keeps repeating this step until the value doesn't change. This is the lowest energy, so it recognizes this as an energy minimum. And then we get further on down some information. So these are the surfaces that we asked the computer to calculate. So the first thing that you'll need to note here are the electrostatic atomic charges. So we see that the oxygen has a plus charge, the carbon has a minus charge. This is giving us an indication of the charge density on the atom. We have some information here on the vibrational detail of the molecule, because remember we ticked the vibrational mode. So this is another term that we'll need to note down, the vibrational frequency. Okay, the other thing we're interested in is the dipole moment, so we can go into Display Properties and we'll see here dipole moment, and you can actually display this in the molecule. If you click Display, this is giving us a sense of the dipole moment in the molecule. We're also interested in the bond length, the equilibrium bond length, so if we just click on the bond here, we can see, I move the screen in a little bit, we can see the bond length value spits out here in the bottom right hand corner. Okay, we can also get a visualization of various aspects of this molecule. So for example, if we click on orbital energies, we get some information here about the orbital energies of the HOMO, HOMO -1, LUMO, and so on. We can click on the surfaces, so we can get the density surface, or we can view the so this is our highest occupied molecular orbital surface, and we can even view the infrared spectrum, because we can find out the infrared spectrum of the molecule. This is the computed infrared spectrum, and if we click on that spectrum, of course there's only one type of vibration here, but if there were several peaks in here, we'll be able to get several, we'll be able to map the various vibration modes onto the molecule. Okay, so what you can do then is go back into Setup, and in Calculations we're going to repeat exactly the same thing, except now we're going to change it to Hartree-Fock, and we can add in 6301 plus G double star. This is a high level of Hartree-Fock, and we can repeat it. What you need to do then is take your data and compare it with the data in the table, and have a look and see how well density functional theory models the experimental data, how well Hartree-Fock models the experimental data, and then choose one of those, choose whichever one you think is best matching the experimental data to model the carbon monoxide cation. So in this case, you're going to have to change when you're measuring the cation, change it to cation, select the appropriate Hartree-Fock or B3 lip, model, you'll have cation, and of course with a cation there'll be one electron less, so there's one unpaired electrons. Okay, so you'll be able to get information on CO for density functional theory and Hartree-Fock, and then you pick whichever one you think best models the data for CO+.